do the introduction so that we can continue. I know time is so much spent. So our presentation today, the topic is about physics of linear accelerator, the principles, and our presenter is Mr. Atul Kumar from a senior medical physicist from the Nairobi West Hospital. Mr. Atul Kumar is a regional safety officer and a medical physicist by profession. He has done post-master's diploma in biological physics from Baba Atomic Research Center, Mumbai, India. He has also done integrated masters in applied physics from Central University of Delhi, India, and some research-related project at the Institute of Plasma Research, Gujarat, India, and the Indian Institute of Technology, Bombay. He has extensive years of experience ranging from 2018 when he began his career as a medical physicist, and where he has experience in medical physics from Tata Memorial Hospital, Mumbai, and a few more centers in India. He's currently a medical physicist, a senior medical physicist at the Nairobi West Hospital. Yes, looking forward to gain more knowledge and to hear from him. So, Mr. Kumar, you can.
Thank you.
Yeah. Okay.
Thank you very much, Fred, for this nice introduction. So let us begin. Today's the topic of discussion is physics of linear accelerators. So this is a brief introduction we will give about this linear accelerator because we are only having half an hour. We'll not go too much into the detail. So as you see, like the GIF in the screen, you can see how the electrons are accelerated. You have got a series of tubes through which electrons are accelerated, and that is why the name is linear accelerator. The electrons are any charged particles, and they are accelerated in a linear path. We call it a linear accelerator. So the linear accelerator has its slide. Wait a second, my slide is not going through. Let me share it again.
Okay.
I don't know why it is not working. Let me share the entire screen. Did I leave? Let me join again. Please admit my email address. There is some problem, I think. Wait a second.
Okay.
CTT. You can use it for chip ion implantation. We also use it for food sterilization and some medical equipment sterilization and several other things. So there are other applications of like you can use LINAC for an injector in synchrotron. Synchrotron are even higher accelerators. You can also use it for like some nuclear treatment purposes and several other nuclear spallation processes as well. But most commonly we use overall in the world is the medical applications of linear accelerator. Most of the other applications are either limited to industry, very limited number of industries or very limited number of research centers. So if we start from where the linear accelerator concept has started, so it was started at around 1924. There was a scientist called Ising. He published a research paper that if we like previous to that we had that KV cathode ray tubes. So cathode ray tubes was a big research topic in 1800s, 1880s, 90s. So then they have already developed all those cathode ray tubes. But now in 1924, some scientist called Ising, he published a research paper that if we can combine two cavities, two cathode ray tubes with a frequency, RF frequency with alternative frequencies, like instead of one anode, we can have two anodes and we can have a frequency inside. That is how we can increase our energy of that acceleration. So although he could not make that, but he used it, he used it just a theoretical way to publish it. Later on in 1926, some other scientists did some research based on his paper, and they successfully have managed to make a linear accelerator. Then Cockcroft and Walton, as you know, they were big scientists who developed those ion accelerators also. So they are the ones, they got it developed, but they are not the first one. In 1926, someone else, I forgot the name, he developed the linear accelerator for the first time. Then Cockcroft and Walton and Rutherford and most of the scientists started working on it. Then in 1952, the first medical LINAC was made. You know, in World War II was a big era of innovation. At that time, all those magnetron, klystron, those radars and all those things were being developed. So soon after the World War, the medical LINAC now can be very easily developed. So in 1952, they have treated one small kid, I think you might have seen that picture, was the first treatment using medical LINAC. The MLCs and other things and those JAWS and those several other things kept on coming later on. In 1965, the MLCs came, like the first idea of MLCs. And in 1982 in Stockholm, the IMRT was first conceptualized. So this is a brief timeline of our medical linear accelerator. So like a linear accelerator looks something like this. If you see, it has a gantry. This thing is called gantry. It has, this is the head. This is a KV generator, KV X-ray generator. This is a KV detector. And this is called EPID. Somewhere here is the center of rotation of this axis, where this axis of rotation coincides. We call this isocenter somewhere here. So this is a linear accelerator, which, as we already discussed, it is a machine to accelerate the elementary particles. These elementary particles could be electrons, protons, or ions. It is used to produce high energy electrons, usually, mostly in medical LINACs, or high energy X-rays. Electrons are usually accelerated using RF waveguide, and they are bombarded to a target, and that target, after electrons bombard a target, they produce some X-ray called Bremsstrahlung X-rays. So these X-rays are very high energy X-rays, which can be used for our treatment purposes. And these X-rays now can be collimated using different collimators, MLCs, and several other techniques for our medical treatment purpose. So this is the gist of a LINAC, medical LINAC. So what is the basic design? So the basic design of a LINAC is like from inside, it looks something like this. So you have a radio frequency source. That radio frequency source can be a magnetron or can be a klystron based on the design of that LINAC. When that radio frequency source is sent to this a metallic waveguide, this is usually made up of very high engineered copper, very smooth copper, and there are several cavities inside it, and that RF frequency is fed inside these cavities, which accelerates the electrons, like the surfing in the sea. A man surfs in the sea by gaining the energy from that wave. In a similar way, it's a very miniaturized version of that thing, in which the electrons kind of surfs the RF wave, that is called traveling waveguide, and there are other ways also, like standing waveguide. And these electrons then gain their energy, and then they are accelerated. And where these electrons are coming from, so the electrons are coming from something called electron gun. We will discuss all these things in detail. So there is an electron gun which produces those electrons for us, and then that electrons are injected inside this cavity called waveguide or accelerating waveguide. That waveguide is already fed with a radio frequency. That radio frequency is usually 3 megahertz, 3 gigahertz or something. And that energy is now used to accelerate this electron. And that RF wave accelerates this electron. This electron then hits a target here after bending through a magnet. It hits a target, and that target produces X-rays. If you don't want X-rays, if you want electrons only, you can directly get an electron outside this. If you want X-rays, you have to make that electrons to hit a target. That target is usually a very high atomic number material, maybe tungsten or something, and then you get your X-rays, Bremsstrahlung X-rays. We will discuss about the physics of these productions of X-rays and all. And then you collimate that X-ray. So how do you collimate? You use JAWS primary collimator, then you use JAWS secondary collimators. Then you can also use MLCs and several other techniques of the movement of MLCs using, like we call IMRT or VMAT. And then we can collimate those X-rays to target the tissue that we want to treat. And after that beam passes through that body, we have got a detector here. This is called EPID or electronic portal imaging device, which can detect about like how much X-rays is coming through, and it is used for several other purposes. So this is a basic design of a LINAC. In some LINACs, you also have arms around, like there are two arms that I have shown in the previous image, which is a KV generator and a KV detector that is used for the proper localization of the patient. So that is an addition to the LINAC. So this is called couch. This is having some movements. It can go up, down, it can go laterally, it can rotate, it can go in and out. So there are several movements to this couch which are used to set the patients very nicely. So this is the basics of LINAC. So the electron generation component and electron accelerating waveguide, these two components, pulse modulators are there. We'll discuss about the physics behind all these things. So first we discuss the electron injection system, how the electrons are being injected in the waveguide. So electron injection is a very simple process, very simple physics. The old incandescent bulb in our houses, now it is replaced by LED bulbs. But if you remember those old incandescent bulbs in which there used to be a tungsten filament encased inside a glass. So the same thing is used here. You have got a thermoionic emission. So whenever anything is heated, some of the electrons kind of boils off the surface, just as you boil your water and you get vapor outside because of heat. Same way, if you heat a metal, some of the electrons will come out of the surface. That is called thermoionic emission, because thermo means heat and ionic means charge. So that electrons get charged because of the heat, and then they leave the surface and they form an electron cloud outside the heated metallic surface. So if you put another electric field, if you put some positive charge outside that electron cloud, so that electron cloud will be sucked to the positive charge, that is the anodes. So that is how those electrons are being ejected from that metallic filament. So this is a very simplistic design, but the only thing you have to keep in mind is, like, those electrons, when they boil off, obviously they will boil off randomly, but you have to focus them. So there are some focusing cups. So those focusing cups are nothing but a positive charge, negative charge of cup, which is repels the electrons to the center, and then the electrons are ejected through the center. So this negatively charged electrode is called cathode, and this cathode, then you have got this focusing cup around it, and then you have got some grids to allow only like streamlined electrons outside, and this is how these electrons are being generated. This is how it looks like. So you have got this grid inside. So inside there is a filament which kind of like electrons then comes out because of this small positive charge which pulls these electrons out. So this is how the electrons are being. So electron injection system is responsible for injecting electrons into the accelerator. The injection system consists of components such as electron gun and a beam focusing device. It runs on thermoionic emission and is controlled by the current of the filament. It ensures a stable and controlled electron beam. So now the current of the filament is very important. When you have a high current, that means the filament will heat to a higher extent, and you will have more clouds. So slight change in the current in the filament changes your output of electrons to a greater extent. So that is how we manage, like that is how it is tuned. Now there is another part of it, like we have discussed about this electron gun briefly. Now we will discuss about this radio frequency source. So this radio frequency source or RF power generation system is very important because it is the thing which is used to accelerate the electron. The RF wave that is being generated is the one which is used to accelerate the electrons. So there are usually two commonly RF power sources. One is called magnetron, the other is called klystron. We will discuss about both of them. So either magnetron or klystron are used. So magnetron is a vacuum tube generating microwave power, and klystron is used to amplify that RF wave. So this is how it is done. So we will discuss about the physics of klystron and magnetron in detail, not very high detail, briefly. So now this is a magnetron design that you can see. In physics, you might have read about the LC oscillator. What do you call it? Inductor and capacitor. If you connect an inductor to a capacitor, and if you send a voltage across it, what will happen? The capacitor will create an electric field because of it. So current, that AC current will oscillate, and that you see, like an inductor is just a coil of wire and a capacitor by non-conducting rails. So if these are very close, they can form an electric field between these two metal plates, and this coiled wire can create an electric field in the system. So this is the basic principles of magnetron. So, and now suppose you also might have also heard about the induction, electromagnetic induction. So when you place another coil nearby, the oscillation in this coil will be transferred to the other coil using electromagnetic induction, right? Because of the changing magnetic field, you will induce a current on the second oscillator, and then that oscillator, that LC, that inductor can now generate RF wave because of the oscillating electromagnetic field. So, but in this simple arrangement, there will be a huge energy loss, and you will not be able to sustain this for long. So that is why a clever physicists have developed this magnetron. So in this system, what happens is, like, the central part is charged negatively, the same as the cathode ray, that electron injector that we have seen. So this is charged negatively and it is heated. So again, the electrons come out from it using thermoionic emission. The same physics that we talked about the thermoionic emission. So now the electrons are thrown out from this, and this side, this thing around it, this disk around it, is positively charged as compared to this centrally negatively charged rod. So what happens? These electrons then kinds of boils off, and they run to this outer disk. But interestingly, they have kept a magnetic field. The magnetic field is shown in blue here. So you can see a magnetic field which is perpendicular to this disk. Exerts a Lorentz force. Lorentz force is usually perpendicular to the magnetic field and also perpendicular to the directions of electrons. So you get a centripetal acceleration force for the electrons, and the electron curve in a circular path. So this is the path. This red line shows the path of the electron that it takes. Interestingly, when the electron takes this path, it just kisses this part of this cavities. So what happens? The electrons kinds of repel an electrons here, like in the metal, and those electron then transfers to the other side because of this repulsion, and this becomes slightly negative and this becomes slightly positive. So you introduce a capacitance in the circuit without putting a metal sheet here. So this cavity acts as a capacitor. Now this small thing that you see here, this small cavity now acts as a capacitor because of the induction of that electric field. The electrons, when they come here, they repel this part, and these electrons then, because this is a metallic conductor, so this electron travel around the cavity to the other part, and this becomes like one side becomes negative, the other side becomes positive, and you introduce a net capacitance here. And during that movement, again, this outer part now acts as an inductor. So this part acts as an inductor, and here you have a capacitor. So this is how, and when you have sufficient number of electrons, this is a kind of coupling of LC oscillator. So the same thing, which is like a diagrammatical design like this, but a complex design like this, works as a RF generator. Now when you attach an antenna to it, like this antenna, output antenna, this entire thing, when the electrons are oscillating inside, they oscillate here, there, like you can take a simile of a swing. So when someone swings, he also throws air around. So that is a mechanical swing. Here it is an electromagnetic swing. So electrons are electromagnetically swinging. So that swing is translated into electromagnetic radiation. So that electromagnetic radiation is the RF wave that we can use to accelerate our electrons. So this is the basic design of a magnetron. You can see this acts as an inductor and this acts as a capacitor. There are obviously several other complicated engineering things attached to it, like these cooling fins, because obviously when electrons are involved, a lot of heat is produced, right? Actually, your microwave oven has this magnetron, a small magnetron inside, and you see how microwave oven can heat things up very quickly. So these heats and other things are now dissipated in this case. Klystron is a slightly different concept of creating an RF wave, or rather amplifying an RF wave, but it's also serves the same purpose. It also gives us the final output is again an RF wave. What we want is an RF wave. So in klystron, what happens is, again, you have a simple thermoionic emitter where you can emit electrons out. When the electrons are being emitted from this thermoionic emitter, they travel to this direction because of, again, positive charge, a net positive charge in this direction. So they travel. All these electrons are kept focused using a very strong magnet around it. So that magnet does not allow those electrons to repel one another, and they travel like a laser beam, like center, and they do not allow any electrons to turn around. And when these electrons are going along this direction, there are maybe multiple cavities, but in the base called the buncher cavity, and the other is called the catcher cavity. So the buncher cavity puts an alternating positive and negative voltage on these two walls. So what happens is, those electrons, obviously those electrons which are going in this direction, some of them are slow, some of them are very fast, but this buncher cavity kinds of creates an alternative electromagnetic field, electric field. So that electric field accelerates those electrons which are slow and dampens those electrons which are fast, because if this is suppose negative, those which have like passed and they reach here, they will be repelled because of this negative charge, and those which are like those which are slow, which left behind, they will be attracted by this wall, this positive wall. So this is how this buncher cavity kinds of create a uniform velocity of all those electrons instead of having a random velocities, different velocities. And then all those buncher cavities, like those buncher cavities, those electrons, when they have equal energies, they kind of accumulate here, and then there is a gap, and then there is another accumulation, like this keeps on going, and when they reach here again, because of their energy, they strike here, and then they create a same RF wave, same frequency RF wave, because they were oscillating here with a frequency, they were oscillating here with a given frequency, so they will travel, and then they will kind of oscillate here again and create an amplified RF wave. So the RF wave which was fed inside is now amplified. So you can think this as a drum, like when you beat the drum, you get a very amplified sound of the frequency that you are beating is now amplified because of that leather of the drum. The same way you feed in an RF wave, and that is being amplified using this other design. Obviously, only 35% of the electron can be converted, the energy of the electrons can be converted to RF wave. The rest 65% or 70% of the energy has to be collected here, and this heats up a lot. So you have to have cooling systems and several other mechanisms, engineering mechanisms. But the basic physics is you have a buncher cavity and then you have a catcher cavity. Because of the same frequency oscillation, this buncher cavity kind of bunches those electrons, and then the catcher cavities now oscillates with the electron's vibration, and that oscillation creates an amplified RF wave. There are some details you can read. Let us move to the next topic. We are running out of time. So there are variable energy and waveguides. Now, the waveguide that we have discussed, that is the main part of the LINAC. This thing. This is the main waveguide where the electrons are being accelerated. So this is the medical LINAC or variable energy for different treatment. Obviously, in medical LINAC, we have separate different energies like 6 MV, 10 MV, 15 MV. So all these energies require different length of waveguides. So they are engineered based on the requirements. Right. So there are various traveling waveguides. So traveling waveguides means the RF wave travels inside the waveguide. And then the surfing example that I have given, like a man surfs on a sea wave, and that wave always accelerates the man because the man is always falling down. But as soon as the man falls down, the wave catches up, and the wave kind of takes the man high up in again, and then the man falls again. The same way, like man is always falling into the gravity and he is gaining energy, but the wave catches up and always lifts him up. The same way, when RF wave follows an electron from behind, those electrons fall in that electric field, but because of the constant RF wave from behind, the electrons again goes to a higher energy state and then accelerates. So those small acceleration adds up together, and then the electrons are accelerated using traveling waveguide. That is a example of traveling waveguide. In physics, there is another example called standing waves. So if you have like a reflector at the end and you throw a wave through it, you will get a reflection of the wave, and both these waves will interact, and you will have an interference, and because of that interference, you will have nodes. You will have nodes and antinodes. That is called a standing wave. I hope like all you physicists must have an idea of standing waves. So those standing waves are also like bunched in different cavities, and those cavities, the way we have seen in klystron, same way those cavities are now used to accelerate those electrons in this case, and that is how this standing waveguide. Most of the variant machine uses standing waveguides, and most of the electron machines use traveling waveguide. This is an example of standing waveguide. If you see, like this is how it looks like from inside. This is a not cross sectional. This is a sagittal view. In like if you compare it with the medical image. So this is a sagittal image of this waveguide from inside. You have got different cavities inside. This is how it looks like. So each unit cell. So when you see like this red line represents like repulsion of electron, and this blue line represents acceleration of electrons. So when as soon as the electrons reaches at one point, they switch their polarity, and then they push the electrons again. So this is how this is achieved in standing waveguides. These are the nodes and antinodes. This is the point. The join where the red and blue joins is an antinode, and there is a node. So this is how the standing waveguide works. I hope this GIF explains it. In the traveling waveguide, you can see how it works. It's different from the standing waveguide, but it's usually longer than the standing waveguide because of the physics it requires. So you have got electron guns, you have got input coupler and then output coupler and those things. And then you have got, this is how the traveling waveguide works. Is it seen in your GIF? Is the GIF playing in the shared video? Can you see it?
Yes, you can see it.
Okay. So let us move quickly. Now, after those, like now we are here. Now we have accelerator of electrons. Now the electrons has reached here at this point. They have reached. So now they will be bent through a magnet. That is called a bending magnet. So what this bending magnet does is there are different types of bending magnets. The idea is to, when the electrons have already been accelerated, the idea is to bend them down and to make them hit on a target. So this is the first type, bending magnet. But you can see because of the mutual repulsion of electrons and the difference in speed. Not all electrons are at the same speed. And you know the Lorentz force of deflection from a magnetic field to an electron depends on the speed of the velocity of the electron also, v cross b. So the higher the velocity, more the force. So more deflection. The lower velocity means less force. So because of difference in velocity, the electrons which were very much centered at a location, they now start spreading. And then they spread and then they hit the target. So they do not create a very nice, because you know the focusing, what do you call it? The diameter of that focus will be very high in this case, and you will not have a very sharp X-ray images or very sharp X-ray production here, you know, because of those penumbra effect and all those things. We want it to be very sharp. So that is why scientists have designed another 270-degree bending magnet, in which the same effect happens, but it kinds of like negates itself, and then you have a very sharp bending here using 270 degrees. Nowadays they have designed this kind of bending, like this 12 degrees of bending. So this does not requires more space. Like this requires a long head crown here in the linac, and then when the linac goes to 180 degree, this is not very easy to pass it through the floor. You have to make some hole in the floor and all those things. So that makes it slightly difficult. So this design is more compact, the design 3. So these are some of the designs to bend the magnet. So nobody uses this 90 degree, either 270 degree or 112 degree. This is again explained. I think I have already explained it. This delta x and the difference in the velocity and difference in the. Now, when the electrons are being bent, they are made to fall on the target. You can see they come here and they fall on a target, and then X-rays are produced in every direction. This is how a target looks. It's a diamond target. It can be made up of different materials, like mostly tungsten. So now, like after steering the high energy electrons, they are made to collide in a metallic target, preferably tungsten, to produce a high energy Bremsstrahlung X-rays. This target removes, in the case we need the electrons. If you do not require X-rays, you can remove this target. This is the typical geometry of the productions of X-rays. In very high energetic, it's like mostly in the forward direction. If it's a low energetic, its shape looks like this. Now after the target, the X-rays you have already produced, you contain all those X-rays in a very small but from all around, and then you leave it to come out through a very small opening slit, and those electrons or those photons, X-rays, can come out from that slit, and then they are made to hit flattening filter. So this cone shape that you see, these two cone shapes are flattening filter. This one is flattening filter free beam, and this one is an electron scatterer. If you need an electron scatterer, you will make your electron fall in this electron scatterer. If you are having an X-ray coming out from that slit, you can make that X-ray to fall in this flattening filter. So what it does is it flattens your beam, because the intensity at the center is higher as compared to the intensity around it. It's like a torch. When you blow your torch, the central part is the most lit one. It's having the highest intensity. But if you put a butter paper on it, you have a more or less uniform light coming out from the torch. The same way, you have to stop the center part to more extent than the radial part. So that is why this kind of shape is used to flatten the beam. Now, after the beam passes through this kind of shape, the output of the beam is now more flattened. So this is why it is called flattening filter. But nowadays we do not want this, because this attenuates the beam to a greater extent. So we are using flattening filter free. We are not flattening it, but there is something other mechanism called beam hardening. So beam hardening should we discuss. Mostly like lower energy X-rays are cut off and higher energy X-rays passes through. So now you have a net higher energy distribution of the X-ray when it passes through this flattening filter. or this filter. Then the lower energy X-rays are not very good for treatment because they will now interact with the skin and they will cause more skin reaction than the actual treatment. You require higher energies. So that is why this filtration is very important. This is now after they pass through, like before that, you have something called beam monitoring system also. This is an ion chamber, a cylindrical ion chamber. Inside it, it is cut in half. And this is a two separate ion chambers. You can see one is this, the other one is this one here. So these two ion chambers run independently from one another, and then they monitor how much X-rays or how much you make sure that you do not give extra dose or two devices independent from one another, so that if one fails, the other one can give a feedback. So those two run in parallel, and then you see whatever MUs that you have planned to the patient. Beam modifying devices, there are primary jaws. I hope all of you medical physicists know about the jaws. The jaws are like bricks and shape. They are motorized, and then the regular size. So the primary jaws is just the slit. I told you, like when the X-rays are being generated, they are covered from all around, either depleted uranium or very high atomic number like lead, or very high tungsten atomic number, high density tungsten are used to cover the X-rays coming to any other direction except a small slit. So that slit is called the primary jaws. That is the primary collimator. Then there are secondary jaws. Those secondary jaws looks like bricks of tungsten and which are motorized. So they come along and then they can form a shape of rectangle or square, whatever you want. After that, secondary jaws, they are made to pass through a multi-leaf collimator, and you can have your physical wedges or customized blocks if you want. So there are various beam modifying devices after you have produced your X-rays. Like this is some of the figures, like the X-ray beam. If you can see an X-ray, it would look something like this, a light coming out. And you can see this is a pyramidal shape. So this pyramidal shape, this is the secondary jaw I was talking about, the bricks that I was telling. So they kind of shapes the your beam here, and then they are made to fall in a flattening filter. So when the electrons, when the photons fall here, you see the central part is more lit, and this thickness is more here. So now these electrons are, these photons are like instead of this shape, this black shape, they become this white shape, the white shape that you see. So that is how the beams are flattened. This is a 3D representations of how the beam looks like, and this is a 3D representation of the MLCs. So how MLCs can take the shape, and you have an output. I try to make it as compact as possible. I hope you're understanding. So this one is a wedge, how a wedge looks like. And what does a wedge do? If you have this flattened beam here, after it passes through the wedge, this is a very thick end on one side and thin end on the other side. So the thick end, like it interacts and it blocks most of the radiation. So you get lesser dose on one side and higher dose on the other side, and you can modify your dose, and you can have a dose gradient which you can use to shape your isodoses. This is physical and non-physical wedge. There are different types of wedges. If you don't know, we can discuss it in the QA. There are electron applicators also. These electrons usually tend to repel one another. So that is why you have to guide them all to the surface, so that you don't like, usually photons do not repel each other. So once you have like made the shape using MLCs or jaws, they just follow the same shape to the patient skin or even to the tumor. But electrons usually repel one another. So if you don't have an electron applicator like this, those electrons will repel one another and they will form a funnel shape, and they are always scattered away from your target. So that is why you need an electron applicator. It can use magnetic field sometimes, or sometimes just like to shape the electron fluency. So the electrons are charged particles of diversion of cells. There are several other systems also. Obviously, you need cooling, you need vacuum pump, because the entire process of that waveguide and klystron and magnetron, everything needs vacuum. Because if electrons are like you have seen in the bulb, in incandescent bulb that we have talked about, you have to encase it with a glass and fill it with a non-reactive gas, because if oxygen or any other reactive material interacts with the electron will die, and obviously they will collide and other things. So everything should happen inside a vacuum system, and to have that vacuum, you have to have a vacuum pump, and you have to have, like, some of the systems like clystrons and magnetrons, they run on a very high voltage, like megavolts, thousands of millions of volts. So those millions of volts, obviously there are chances for sparks, like the lightning effect that we see. So to prevent that, you have to have a very good insulator gas. So that is SF6 is used as an insulating gas. You have to have water cooling systems around, because this LINAC heats up, because those electrons and clystrons that we talked about, when the only 35% energy is turned to RF wave, the next 60%, 65% is converted to heat. The same thing happens to the anode. When the Bremsstrahlung production, energy production happens, only 0.1%, or in high energy LINAC, maybe 5 to 6%, 8% is converted to X-rays, and the 92% or more is converted to heat. So to cool that anode and several other things, you need cooling system. You need pneumatic drive system. If it is a tomotherapy, or motorized system if it is a normal LINAC. You need head sealing and other things to prevent radiation leakage. So there are several other auxiliary system attached to the LINAC. This is a typical design of a LINAC. If you look closely, you have got your pulse modulator, which gives a pulse of radiation to RF wave to microwave, or magnetron or klystron, whatever you have. Then this RF wave is now fed into the RF system. You have got an electron gun, which is bent through here. Then you have got your primary collimation here, secondary collimation, you have got your platinum filter, you have got your ion chambers, you have got your MLCs, couch, and several other things. That's all. Thank you. Thank you very much. I took a little longer than anticipated, but I'm now open to question and answers.
Thank you. Thank you. Thank you, Mr. Kumar, for that wonderful presentation. I would like, if you have any question, you can write them in the chat box, or you can ask. You can raise your hand. Gloria, I saw Gloria. You can ask your question. Hello, Gloria. Are you there?
Sorry, I clapped. Gloria is saying, clap.
Okay. Kapis, Mr. Kapis.
Copies.
Oh, thank you so much, Bwana Atul. I think that was a very good presentation. So you talked about the LINAC, the production of the energies. The question that I have that probably you could illustrate is how we get different energies. What really is the factor that make us be able to get, like, for example, 6 MV, 8 MV, 10, 15? What is the main factor that determine the ability to get different energies? And probably you could explain why in CyberKnife we can't have more than 6 MV in most of the times. Thank you.
Most of the LINACs, which are bigger in size, like TrueBeam or Versa HD, they usually have a longer waveguide, right? So there you have an option of different standing waves and different like length of traveling waveguides that you want. So by in traveling waveguide LINACs like Versa HD or those from Electa usually use traveling waveguides. So you can extend your traveling waveguides and you can increase your energies. And in standing waveguides like TrueBeam and others, you can use different standing waves, like the different nodes of the same RF frequency to use different energies. Like, for example, you must have known about the lambda by 2, lambda by 4, and these different standing waves, right? So if you use different standing waves, or if you use a longer traveling waveguide, you can increase your energy of the acceleration of electrons. That is how we change the energy of the electrons. And your question about the CyberKnife, for example, why do we have single 6 MB energy? So CyberKnife is a very compact LINAC. Like apart from the out of the bigger design of the CyberKnife, majority of the design is the robot. And only the head of the CyberKnife that you see is the LINAC. So the size of the LINAC as compared to the entire size of the CyberKnife is very small. So it's a kind of LINAC grabbed by a robot. A robot is grabbing that LINAC. So that LINAC has to be very compact. So because it is very compact, so you cannot have like different longer wavelengths for your traveling waveguide, or your standing waveguide cannot have different nodes, because those are to be designed very precisely, because these are engineered with nanometer of scaling. Like very precise scaling is required because you're dealing with electrons. So for those smaller compact LINACs like your CyberKnife or tomotherapy is again a very compact LINAC placed on a ring, or Halcyon that we have here in Nairobi West. So those Halcyon, tomotherapy or CyberKnife, they are very compact LINACs, and that is why you do not have those scope of different waveguides. You do not have that scope of bending magnets either. Like those bending magnets are also like play a vital role when you have different energies, different quadrupole magnets are used. So like they do not have bending magnets. They just have a straight electron accelerator, very small compact electron accelerator coming directly to hit the target. And then you do not have enough scope for all those carousels and all those things. Like obviously if you are having different energies, you'll have to put different flattening filters. You have to put different electron scatterers. So you'll have to have a carousel. So that will increase your size, which you cannot afford in CyberKnife or tomotherapy or Halcyon. So these machines are explicitly designed for compactness. So that is why you have only single energies. But those machines which are designed for higher energies like TrueBeam, Versa HD, Edge, and there are several other machines, they have multiple energies.
Thank you so much.
Ian or Evans.
Evans?
Just to add, thank you very much, Atul, for that great presentation. That was wonderful. I just want to add that most of the time, for you to be able to have different energy, they usually vary the RF. They actually vary the RF. And then, Kapis, your question on CyberKnife, why they don't use high energy. I just think, I'm not saying what Nania said is very correct, but just in addition to what he said, I think most of the time is because most of the algorithm still don't know how to take care of neutron activation that will come as a result of high energy. So because of that, they limit it to a little bit lower energy in order to prevent that. Thank you very much.
Okay, I will just want to add your observations of the neutron contamination in the beam. I have done a project on neutron contamination, that is why I think I am in a good position to answer this. The contaminations of neutron is very minimal, 0.07% or something of the dose that we receive. So obviously, like when you have higher energies, you have to kind of take care of those neutrons and other things. And what you can do to do that is, like, neutrons usually activates the metals that are used to shield the photons. So because of that activation, you get some another extra energies from in and around. But most of the activations are very short-lived, like few minutes. So if you wait for like 5 to 10 minutes, most of the neutrons or the activation X-rays, activated gamma rays that are coming from because of the neutron activation usually dissipates. So that is like, obviously we do not collimate our neutrons even in TrueBeam or in Versa HD or higher energy LINACs. We do not care about the neutron dose, although we care about the neutron contamination, which can cause dose to the staff. because that dose to the staff is very limited. You cannot afford to have more than 20 millisievert in an year. But for the patient, the contamination of neutron is not very significant, is like only less than 1%, 0.07% or something. I calculated. I even one of my teacher, we have done Monte Carlo simulation for the contamination of electrons, and we have also verified that using gold activation, and I have also done one DLD based neutron measurements. So there we have not found like various very high contaminations of neutrons. But yes, what did you say? Yes, the neutron is a factor when it comes to higher energy Linux. Thank you.
Thank you very much.
Thank you. Mr. Ian?
Hi, Ian. Yes.
Move to Oren.
Hi, team. Thank you, Atul, for the wonderful presentation. I have a few questions to lay across. So one, does low energy utilize the RF from the magnetron, while the high energy they utilize the RF from the klystron? Thereby seeing it like for the variant machines, that is the modern Linux, we have both the magnetron and the klystron, while for this cyber knife, we only have the
magnetron, yes.
Magnetron alone. And what is the concept behind that? Then another question, what is the noted difference in functioning between the variant machine and the Electa machine based on the fact that they have different waveguides, whereby the Electa has the traveling waveguide and the variant machine, they have the standing waveguide?
Okay. So to answer your first question, like why do we have magnetron in CyberKnife, or usually in single energies machines, we usually use magnetron, and why do we use klystron in higher energy machines? So the concept is very simple. The magnetron can produce an RF wave, and that RF wave has a fixed frequency based on the design of your magnetron. So when you have a single energy machine like CyberKnife or Halcyon or tomotherapy, the single energy machine, the 6 MV machine, only utilizes one RF frequency, right? So you need only that much RF frequency, and magnetron cannot produce very huge intensity of RF wave also. The intensity of RF wave is also not very high. To have a very high intensity of RF wave, you need to have either very high energetic magnetron, or klystron is an amplifier, so it amplifies the wave, right? So when you like are having a high energy wave, like someone asked about the changing the energies. So how would you change the energies? So you will keep your frequency the same, but you can amplify your amplitude of the wave. So higher amplitude means what? Higher energy for the wave, and higher energy for the electron to get accelerated. So when you amplify your wave, you get your amplitude higher, and to amplify that, you need a klystron. So klystron is a very nice invention to amplify your waves. So when you have a magnetron, it produces the RF wave that you want, and then klystron can amplify that wave when you want to use it for higher energies. So that is why most of the high energy machines uses klystron, and the single energy machines uses magnetron, because once you are producing your RF wave and you do not require to amplify it, you are good with a magnetron. And magnetron is comparatively cheaper as compared to klystron. That is one thing. The second thing you asked, like why Varian uses standing waveguide and why Electa uses traveling waveguide. So it has to do with the like competition. I do not know very correctly, but I think like there is some patent related issues. Varian were two brothers in America. One was in army, and he was the one, I think, who designed this klystron and all those things. And he had his patent, and that is how the Varian company started. The other brother was engineer. One of them was working in military. So he was like trying to make radars. So radars, you have to have your RF waves, those microwaves and all those things for radar. And for radar, microwave magnetrons were used to produce those radar frequencies. But I think this Varian brother, I'm not very sure, but I think I read it few years ago. The Varian brothers, one of the brother, then he designed this klystron, how to amplify and all those things. and he used all these standing waveguides. So it has to do something with the patent or the industrial competitions. It's like one company using something, then the other company comes up with something else.
So, having worked with the two machines, can you give us any notable differences on the functioning of the Linux themselves?
Yes, you can see a very big difference. Like in most of the variant machines are very compact. Even TrueBeam, if you see, is just 1.5 meters long, the waveguide, 1 meter, close to 1 meter. But Electra machines like Versa HD, you have seen, you need to have another separate room behind that LINAC,
Yes,
right?
sure.
And the waveguide is very long. So if you have a traveling waveguide, it's very long. But if you have a standing waveguide, you can compact everything, especially your waveguide, right? So the Electra is usually bulkier as compared to Varian.
Yeah.
That is the biggest change that you can see. The second thing that you would see is Varian is having like better user friendly. I would say Varian, I have found it more user friendly as compared to Electra.
Thank you.
Thank you.
And then Daniel Warul.
Hello.
Yes, hi.
Okay, thank you, Mr. Tut, for the presentation. So my first question is, in the data rooms, we have the H-box that are used for neutralizing the neutrons. Is it therefore advisable to utilize 15x and 15x in VMAT and IMRT planning? Or
See, so your choice of your beam depends completely on your patient. If the patient is very bulky and your tumor is very deep, you should be using higher energy X-rays, 10 MV or XMV, depending on your patient. But yes, obviously, when you use higher energy X-rays like 15 MV or 10 MV, you will have to also cater for the neutrons contamination that is coming. And while commissioning a LINAC, we also measure that percentage of neutron contamination. Right, we place neutron detectors at several locations as guided by the regulatory authorities. So we place them and we see how much is the neutron contamination. And the second risk comes with the activation, neutron activation. Those neutron then go and collide with tungsten or some sulfur or some nitrogen inside, and then they create some secondary radiations coming from some activated materials. So if you are using 10 MV or 15 MV, it is always advisable to enter the room after 10 to 15 minutes of the, like 5.
okay, also the other question. Hello?
Yes, you can ask.
Linux, we don't have the KVMs fitted. And you find that we normally see that the CBCT is normally fitted in the Linux. Is it possible to have...
Hello? I cannot hear you. Can please come again?
I'm asking this. In some Linux machines, you don't have the KVMs fitted. But in the theory, we normally study that the CBCT is normally fitted in the Linux. Is it therefore factual to say that a Linux that does not have the KVMs does not have the CBCT technology incorporated in it?
No, like for our machine, like the one machine we are using is a Halcyon, and we do not have KV, but we are using MV CBCT. So you can use your CBCT using MV as well as KV. In most of the machines like TrueBeam, I think the MV energy which is used for the imaging is 2.5 MV. And the one which is used for treatment is 6 MV. But in some LINAC like ours, the same energy which is used for treatment is used for MV CBCT. But if you have a KV arm, obviously it is better imaging as compared to MV. But but you can have your CBCT both using MV or KV.
Okay, and also when you have the CBCT and you want to conduct maybe adaptive radiation treatment, now the images that you pull from the CBCT, once you pull them after maybe a certain duration or after a certain number of fractions, is it wise to conduct a rescan CT, or you just utilize the deformable image registration? That is the images.
No. You should be doing a resimulation, because your resimulation will obviously depending on, like, if you are doing an adaptive radiotherapy, obviously your tumor has changed or the patient size, weight has changed or something has happened. So then it is always advisable to go back and do a resimulation. Because those CBCT, the CBCT, the term itself is cone beam. It's not as good as the fan beam of the your diagnostic CT. But nowadays these technologies are coming. There is a software from Varian called Velocity. What it does is, the day it takes the CBCT, and those CBCT images are so good that it can superimpose your plan on that CT of the day. And then you can have your plan, like MR-Linacs and all those technologies are coming. But for the technology that are available right now, it is always advisable to go back to your simulation, do a resim, do a replan if you are doing adaptive.
Okay, thank you.
Gigi, if you can.
Sorry, I was.
Yeah, I wanted just to ask a very quick one. Thank you for your presentation. But I think the only area tool you have not clarified is about the neutron. Very well. You said you have to. It takes like how long?
Like 10 to 15 minutes.
Yeah, and practically we can't wait 10 to 10 minutes or 15 minutes to get in. I think. So that's need clarification, because it conveys a bit of eye blue. I thought it's around 10-15 seconds or something. Yeah, just find out. Maybe we get it clearly.
Obviously, it's an exponential decay, right? So for the first few minutes, it will be very high radiation. So you should not go like within 1 to 2 minutes for sure. But if you want a very safer, like if you're treating like usually the bunker design that we calculate is like 70 patients a day with 6 MV or 35 patients a day with 15 MV. The reason is the same, because when you design a bunker, you also keep in mind that waiting time that you are saying that comes there. So like 5 minutes you treat a patient, then 5 minutes you wait. And that is why you have to have like 35 patients only in a day if you're treating with higher energies. But yes, 10 to 15 seconds, the radiation will be very high, very significant. But even if you go after 2-3 minutes, you just do an experiment. If you have a high energy LINAC in your unit, just fire a very high energy X-ray, 15 MV or 10 MV, and then put a survey meter there and see the decay. Like after 2-3 minutes, it will continue. And if you are like doing 30-35 patients every day with higher energies, then it is advisable. Like I, as an RSO, will advise to go after 5 minutes if you are having that many number of patients, because that will increase your dose to the RTTs to more than 20 millisievert. The neutron doses are not that high. Neutron doses just diminishes within 10-15 seconds. That's correct. But the secondary activation that I'm talking about, those have like few minutes of half-life. But we can discuss.
Thank you.
Okay.
I think the next time I will take this topic of neutron contamination in LINAC. Okay, and we will discuss it in detail.
Beautiful. Thank you.
Okay, just a quick one. Thank you, Mr. Trul, for the wonderful presentation. Between the flattening filter and the collimator setup, which one comes first in the LINAC assembly?
The primary collimator comes the first. You have got that primary collimator. That is the first thing.
Yeah.
Right. Then you have got your flattening filter.
All right.
And then you have got your secondary collimation, those jaws and
All right. And then now there are MLCs after that.
MLCs after that.
Okay,
But
fantastic. Thank you.
some machines, I think one of the Siemens machine, the MLCs was put before the jaws, but that is not a very convenient and good idea to do.
Okay.
Most of the machines
Alright.
MLC later.
Okay, so thank you so much.
Okay. Okay, thank you. And there is a question from inbox.
Okay.
I read for the three types of wedges mentioned to modify the beam. Are they all placed in the LINAC or LINAC as one that is either the physical wedge or the dynamic wedge or the virtual wedge? And are they all the ones referred to primary collimator? Is a question from one of the.
Let me also read it. I did not get the question very correctly, I think. Let me see. I beg to leave, sorry. For three types of wedges mentioned, modify the beam. They are all placed in LINAC or LINAC has, that is either the physical wedge, dynamic wedge, or the virtual wedge. Okay, so let me just briefly tell you. Previously, when it was the era of cobalt, we used to have a physical wedge. We used to keep a physical wedge in between the teletherapy machine and the patient. But now later on, Electa came with an idea of motorized wedge. Motorized wedge means they physically put a wedge inside the LINAC, like the jaws and MLCs are fixed inside the LINAC. They have fixed a wedge inside the LINAC, and that wedge was of 60 degrees in angle. And if you want a 60-degree wedge, you will put that in place and you will have your radiation. You will have your beam as a 60-degree wedge. If you want only 45 degree or 20 degree, 25 degree or 30 degree, whatever wedge angle you want, then that the Electa used to divide that time. For example, if your treatment goes on for 2 minutes, for the first 1.5 minutes, for example, there will be no wedge, and for the last half minute, there will be a wedge with 60 degree. Adding both these together, they will add up, maybe say for example, to give a equivalent wedge effect of 15 degrees. For example, so they did the math. The math is not very difficult. It has to do with tan theta, tan 60 degree of something and all. What the wedge that you want and the wedge that they have put, you have a ratio of the tan theta and all, and then that is how you calculate that was called motorized wedge. So that was, but then later on somebody came with a brilliant idea, like if you can have a wedge and which comes in place and goes out of place, and then they create an addition of wedge effect, why can't you simply use your jaws for the same purpose? You just drag your jaws slowly in the field. So what happens is, like when the jaws are coming to cover the entire field, what happens, like the first part of the field is covered first, and then the jaws move like inside the beam. So now more and more beam is being covered by the jaws. So the first part which was covered earlier is covered for most of the time, and then subsequent parts are covered for lesser times. So like because of the difference in exposure of time, because the jaw is moving, you have a wedge effect. So this kind of wedge effect is called dynamic wedge effect. So that you don't have to put a physical wedge, you don't have to put a motorized wedge. You can simply create a wedge effect using a moving jaw while the treatment is being on. That is called dynamic wedge. That is what is used. I don't know about virtual wedge, but this is like physical wedge, motorized wedge, and dynamic wedge. So right now, Varian is using enhanced dynamic wedge, EDW. So it has its own graph called STT graphs and all, which gives you how much time or how much speed the jaw should have to create what kind of wedge effect that you want. For example, if you want a 60-degree wedge effect, obviously it has to move more slowly, because one place will be more experiencing more radiation, the other place is being blocked, and then that moves slowly, so it creates a gradient of dose effect. That is what the dynamic wedge is.
Thank you. Just to add, is the same. The virtue is only the vendor's approach in the determining the dynamic and the virtual wedge. So it's the same. It's the jaw creating the wedge effects. That's how I understand.
Okay, virtual wedge I do not know about. Like I have not heard about it. I know it as what dynamic wedge or EDW, enhanced dynamic wedge.
Yes, they say it is between recti and so some you call it virtual, others call it dynamic, because it's the wedge effect from the jaw. That's how I get it. Maybe we can review it.
Okay, thank you for this insight.
Lawrence, if you have another question?
Yes, Lawrence, if you have a question.
Sorry. Let me put my hand down.
Okay.
Thank you.
So do we have any other question? I believe Kumar has actually tried to answer all the questions very well. Is there any other question or we can close? So if there is no any other question, I want to thank very much the people who have attended. And Atul Kumar, that was very, very good. We still accept many presentations from members. We really appreciate your time.
Thank you very much for giving this opportunity. Actually, I also want to thank Ian for asking, and hopefully I have tried to answer all your questions. Two things we can discuss later on. Maybe one is neutron contamination, and the other one is how do you use amplification.
Okay, I think that is good. Maybe just to mention that in the future presentation, we'd like to see your faces because we want to now create something like YouTube, whereby these presentations will be posting them as videos. So maybe
that would be great.
The future presentations, we would like to see your faces, and even members, if you have a strong network, I think that would be very good. Otherwise, I want to thank everybody. Let's meet next month. Thank you all.
Thank you so much.